بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العلی العظیم. Last session we discussed about the preliminaries about Jacobian and differential kinematics for analysis in the robotic serial robotic manipulator. Today we will start officially deriving the Jacobian matrix in a general form for a serial manipulator. There are two methods in this respect. One method will be given in this session, and the screw-based method will be discussed hopefully in the next session. First, as we discussed before, the Jacobian is a forward map to map the joint space differential variable Q dot into the task space differential variable X dot. If Q dot is given, the relation between Q dot and X dot is simply defined by a matrix, by a Jacobian matrix, in which the Jacobian is the same as all the Jacobian we have in the mathematics. It comes from direct differentiation of the forward kinematics. If we directly differentiate the forward kinematics to find X dot in terms of Q dot, for each component Xi, we have Fi, one nonlinear function, and if we define the derivative in terms of the partial derivatives, the Jacobian can be derived from the direct differentiation and finding the Jacobian matrix of the function f. But usually this is quite hard. It is possible to do that, but it is quite tedious to make all the differentiation by hand and find the forward kinematic map and do the differentiation. We prefer to do it in a more smart and appropriate way, which also provides us with some physical concept and insight to the motion of the manipulator. Anyways, and considering this in mind, today we are looking into finding the ways to generally find the Jacobian matrix for a serial manipulator. Of course, any forward map has an inverse map, and this matrix, since this matrix is could be completely find the inverse of this matrix. If it is a squared matrix, the inverse is defined. If it is not squared, we have a pseudo-inverse. We will discuss it in the future session quite extensively, and what the properties of the inverse would be considered. Okay. Now let's start with a very simple problem of 2R manipulator. We discussed that before last session. I'm just repeating that, reviewing that. For the 2R manipulators, the forward kinematic map has been found easily in the previous chapter. And with the shorthand notation, we have XE and YE represented by these two relations. Finding the Jacobian is directly differentiating these two equations with respect to time. The time derivative of these two will result into theta dot 1 and theta dot 1 plus theta dot 2, considering that Q dot is theta dot 1 and theta dot 2, and by factorizing it, we come across to a Jacobian matrix, which is a 2 by 2 matrix, since our Q and X, both of them are with dimension 2. The Jacobian matrix is a 2 by 2 matrix. It is not very easy, but it is quite naturally derived we cannot still think of what is the physical meaning of the first row or the second row if just differentiating it, but there are some physical properties there. As I mentioned, the control students are quite familiar with linear algebra and the benefit of using matrices in the manipulation and mappings. Any matrix could have some eigenvalues, eigenvectors, singular values, and and the norm of this matrix, the determinant, the transpose. Each of these mathematical representation has some physical insight and meaning in the Jacobian. To address that, let me start with changing the frame of representation. This frame of representation, this Jacobian, has been defined from the base frame, zero frame. We first consider that for a general manipulator, 6 by 6 or even larger degrees of freedom, 3 by 3, 6 by 6, or 7 by 6, depending on the number of actuators and the number of degrees of freedom that we have. Usually Q is given by Q dot, in which, as we discussed by the primary joint, Q dot is defined by theta dot I as for a revolute joint, or D dot I for a prismatic joint. So since we have a series of joints in a serial manipulator, the Q could be generally defined by the Denavitt-Hartenberg parameters or the joint variable parameters that can be actuated by the actuators. So the number of them could be depending on the number of actuators that we are using. If we have a fully actuated manipulator, then if this is 6, for example, then our velocity and the angular velocity of the task space variable, chi dot, as we discussed last term, would be basically, we call it V dot or chi dot. Chi is better because it is not a 3 by 1 vector, it is a 6 by 1 vector. Usually we have 6 degrees of freedom for a general manipulator. It is composed of the velocity of the end effector and the linear velocity of the end effector and the angular velocity of the end effector. In most cases, the end effector, the point at the end point of the robot, is of interest. But sometimes, as we discussed in forward kinematics, we consider the wrist also as an important point, not only the end effector point, the last point. Maybe sometimes we consider the wrist also in our formulation. It is also possible that instead of using E, we use the W point for the variable that we require. In the schematics that we had before in forward kinematics, we used the P and Q points. The Q point was related to the end effector and the P point was related to the wrist. It is quite possible to find either of them, and this means that we will find the mapping between the velocity of the joint to the velocity of that point of interest. Anyways, any point of in any point, if we consider the velocity vector on top and the angular velocity of the end effector at the bottom, this is the usual or conventional way to find the Jacobian. But if we consider the screw axis definition, that the screw coordinate definition that we discussed last session, we had the angular velocity on top and the linear velocity on the bottom. Just a change of concatenation of them. And as we see, this had some physical intuition, like what the Schall theorem says, and how we define it, we call this a screw-based Jacobian. So the screw-based Jacobian that is defined by this vector is somehow in the format of appearing and presentation different from the conventional Jacobian, but actually we have only changed the rows to find the Jacobians here. Let's start with the conventional Jacobian. The important point is that Q is always given, and the G dot or the X dot is the velocity, angular and linear velocity of the end effector point, either in this representation or in this representation. And the Jacobian also can be somehow partitioned into two parts. We have a total Jacobian matrix. Suppose that this is a 6 by 6. We have a 6 degree of freedom manipulator. So n is equal to 6. We have also 6 parameters or variables here. By this means we have a 6 by 6 Jacobian that relate Q dot to X dot. Now, this Jacobian can be partitioned into two parts. We call it J sub V and J sub omega. J sub V is the linear part of the mapping, how Q's are related to the linear part or linear velocity of the end effector. And J omega is related to the angular velocity. And sometimes we just find partly these two Jacobian, sub-Jacobian parameters. All right, this gives all the notation and definitions that we need to know. For now, we start with, in this session, we start with this type of representation. In the next session, we discuss with this type of representation. And the last but not the least, before giving the the general method to work on that, is how we can go from one frame to another frame for the Jacobian. Since we are working with a 6 by 6, generally a 6 by 6 matrix, or a more than 3 by 3 vector, as you see here, usually we can have this representation if we have the Q dot and X dot both at the reference frame. If these are all both on the 0 frame, the Jacobian is found on the reference frame. So we have a Jacobian matrix represented in the reference frame. But this could be represented in any frame. So Q could be represented in the first frame, second frame, or usually, which is more important, at the last frame, which we call it the N frame. If this is also the N frame, if we represent both the Q and the G in N frame, since there are two vectors, they can represent it in any frame, then the Jacobian is also defined in the N frame. We use the upper superscript, left upper superscript representation to give the basically the definition here for the representation of the frame representation here. But how this could be transformed from 0 frame to N frame, very simply by using the rotation matrices. Since any vector VA and VB, the velocity and the linear velocity and angular velocity can be represented by a rotation matrix, can be transformed from a rotation matrix from frame B to frame A, then the Jacobian can be also from one frame to another frame, can be simply transformed by a concatenation or a diagonal matrix that has R, A, and B in the diagonal form and 0 on the off diagonal parties. By this means we can find any Jacobian in any frame. But why I am talking about representing in different frame? because it might be much simpler to find the Jacobian in a particular frame, and it could also provide us with some better intuition, and better physical intuition, as I mentioned in the next slide. Okay, let's try to find the same Jacobian that we find in two previous in this previous frame as a Jacobian matrix that was found basically quite extensively in the frame 0. Let's try to find this Jacobian now in frame 2, the last frame, and see what is the difference and what are the invariant properties of the Jacobian. What will be changing and what will be not changing in the representation. So we have the same thing, Q dot as theta 1 and theta 2, G dot or X dot also the same thing, but we have the Jacobian in 0 frame. We use, since this is a 2 by 2, it has only the linear part, since it is not a 6 by 6, it's only a portion of the Jacobian. We have only JV here. So we can just multiply it by the rotation matrix. The rotation matrix, if it is multiplied to that, then the Jacobian will be somehow shortened and simplified from this general form to this form. You see here we have S1, 2 and S1, but here we have only S2 in the representation. And very interesting, the theta 1 is not coming to the picture here. So if we sit on here on this part and see the velocity, the change of velocity of the end effector as a function of changing theta 1 and theta 2, basically theta 2 will come into the picture quite easily, as you see here, but theta 1 will be disappearing. Is it true? Is it right? Or is it not right? This will give us some more thought on the Jacobian. Jacobian is a mapping between the velocity of the end effector and the velocity of the joints, and how we can represent it, in which frame we can represent it. The main characteristic of this Jacobian matrix must not be changing. Let's try finding the determinant of this into two different frames. Although the representations are quite different, and this is much more simpler. You see that if we find the determinant of this matrix, just multiply this by this and then simplify, you find these two terms are going out, and these two terms, we have C12, S12. This will also reduced to L1, L2, S2. Again, the theta 1 or Q1 is not appearing in the determinant of the Jacobian. And if you find the determinant here, this is much simpler, because you have a 0, the determinant will be just these two together, multiplication of these two together, which is the same as the other one. Very interesting, isn't it? This representation will provide us with much more simpler manipulation or calculation of the determinant. And you know that determinant have some meaning, physical meaning for a map. If you have a matrix map, changing a vector to another vector, the determinant somehow shows how we are enlarging what is the gain of the system or the norm of this mapping. And you see that regardless of which frame we are representing this Jacobian, the determinant is an invariant property. It's not, it will not be changing. The same thing will happen to the eigenvalues, eigenvectors, singular values, the important inherent physical property of that. And also determinant gives us some more important thing. Determinant is related to some other thing. Anybody can contribute here? We have Zahra with us? No. Determinant. Where we use determinant? Usually determinant will be used in the inverse of the Jacobian. If you find the inverse of the Jacobian, and as you see, the inverse of Jacobian was very important. The inverse was the inverse map here. It is important and has some physical meaning. I will give this physical meaning. Don't worry about it. The determinant, if the determinant is equal to 0, then this Jacobian matrix is singular. It is not invertible. We cannot find the inverse. And as you see, the inverse of the Jacobian would be find where sine of theta 2 is equal to 0. And it is very interesting. Sine of theta 2 is equal to 0 when this arm is fully extended or fully folded. Do you remember these two issues in kinematic? It was the workspace, the border of the workspace, where the solution becomes a double solution, you know. And we get quite interesting relation between forward kinematics and differential kinematics. Forward kinematic properties and also the Jacobian properties, just by the invariant properties of the Jacobian. And this doesn't really change in which frame we are representing the problem. So in many cases, it is very smart. Instead of finding the Jacobian in 0 frame, if we could basically find it from the beginning at the end frame. It was very easy to say that instead of having these two vectors x dot and q dot in the frame 0, by definition, by the beginning definition, we find them in the frame n, for example, frame 2. The velocity of these two in frame 2 representing x dot e and y dot in frame 2, then it would be naturally and without any further manipulation we could come to this Jacobian in frame 2. And we could understand some physical properties of the robot by these two. For now, we are just talking mathematically, but remember that we have a linear algebra and matrix formulation with us that will help us quite a lot to find different meaning here. Anyways, this is the most important issue that we have here now. Let's try to find the Jacobian in terms of a general formulation or general derivation method. And again, we use it two ways. One way based on Denowitz-Hartenberg parameters, and the other way, which is much more interesting, based on the screw-based Jacobian and screw axis definitions. Any questions so far? Yes, Mohammed Mehdi has some question, please.
May I ask some intuitions about Jacobians right now, or it could be better for...
Why not? Yeah, we will talk about it a lot, you know, don't worry about that. But giving the question is no problem. Maybe I don't answer it right now, but thinking about it is very important. Okay.
Thank you. What happens exactly when we change the frame of Jacobians? For example, in the preceding example, we change it from the base frame to the second frame. Does it demonstrate we show the velocity of end effector in which frame? For example, the first.
Exactly.
Now, when we change it to the second frame, it was from 0 to the rest point, or in y2, I can't see it exactly, or in the y1x1.
This is x2, x1.
We showed in the
second frame. Second frame is x2 and x here at the end effector point.
All right, and is it quite right to say that we have a speed with respect to this frame? I think shouldn't it be always 0 or something like that?
Yeah, I can say that. I could understand what is. You have some mechanical background here that will. We have. Let me answer you if I correct. The answer of Muhammad Mahdi is it right to say the velocity of the end effector with respect to the same moving frame? Is it possible to do that? To make sure that you are not misunderstood, at the beginning of this previous session, we defined the relative velocity and absolute velocity. We said that if we say relative velocity, we're considering sitting on the frame, on the moving frame, and seeing the change of the variable or position on that frame. But here we are not checking the relative frame. This is not of our concern. We have an absolute velocity of this frame. You see, when we have a point here moving, if θ1 and θ2 is moving, we have velocity in this direction, a velocity in this direction, two component, and then particularly we could have a velocity vector here. We have an absolute velocity vector here, instantaneous. This velocity vector could be represented in this frame, or in this frame, or in this frame, or in any frame that you want. So we find the absolute velocity. The absolute velocity is a certain fixed velocity of this vector. You can find it any means, any ways that you can find. We will discuss it in the next section, how we can find it. And we have defined it, we have find it here. The absolute velocity has a component x dot e. In this way, it has here, one component here, one component here, so it has a velocity in this frame. But this velocity, when you consider it in this velocity, now you can represent it in any frame. You can represent it in the second frame or in the first frame or whatever. And if you represent it in the second frame, in this frame, it becomes much simpler. In that frame, in 0 here and here, we have two components here and here, which is related to θ1 and θ2. But when we represent it in this moving frame, don't consider the relative velocity, the absolute velocity. If we consider it in this two frame, it is much simpler. You see here, we have S12 and so forth. Here we don't have S12, we don't have θ1 and θ2. And this is correct because you see, when you are representing in this frame just have a θ2 motion from this frame, and the velocity of this physically, if you mechanically distribute the velocity term here, should not really depending on θ. Where we are moving doesn't change the velocity here. Basically, the linear velocity here we are moving or here we are moving doesn't change. But in terms of 0 frame, of course, the component will be changing. So, answering you in short, consider absolute velocity of a point. It is a vector. This vector could be represented in any frame, not only 0 or 2, any frame. And 2, 3, n for whatever. And the representation just will be changing by the rotation matrix.
Thank you.
Any other questions? All right, let me go through the task of finding the general vector. Of course, I don't prove it here. I just give the procedure. I have also written a program for it. I will provide the programs for you to not just use the program, but try to write your own program to find the Jacobian matrix for any serial robot that we are defined. We consider that very simply, it is very, very, very interesting, and it has a lot of meaning here. I cannot right now talk about the meaning. I just give the presentation here, and then later in the next session we will talk about the meanings as well. Suppose that we have some sort of a manipulator with n joints. It can be represented in any convenient or inconvenient method. We can have offset, we can have anything. We can have any sort of de Navier-Sternberg representation, any point of interconnection that this joint have with each other. And of course, we can represent the ZI joint. This is using the de Navier-Sternberg method, but conventional or Paul method. Any frame theta 2 is with respect to Z1, theta I with respect to ZI1, I minus 1 as you remember. And this goes to the Zn, which is the end effector. The point that we would like to find the end effector, this mapping or this Jacobian, it should be assigned first. Either we work at the very end point, for example, this point, or the point here that we would like to find the velocity, or might be some risk point, depending on the case. If now considering that this is the point of where we would like to find the Jacobian for that, we call it ON. If we would like to find this, the Jacobian matrix is proven to have to be defined by a number of columns, which we call it J1, J2 to Jn. First of all, we know the dimension of this. The dimension of Jacobian comes from the dimension of x dot and q dot. So if q, we have 6 degrees of freedom, we have 6 actuators, this is q6, and if x is also a general motion in the space, it is 6, therefore the Jacobian will be a 6 by 6 matrix. And consider in this example, we have 2q and 2x, then we have a 2 by 2 matrix as a Jacobian. This is considered for a 6 by 6 matrix for a general case. Of course, if we have only 2 by 2 or 3 by 3 or 4 by 4, it would be a sub-matrix of that. Some part of this matrix will be equal to 0. We consider it for a general derivation, for a general case. So it would be a 6 by 6 usually, since we have the x dot as a 6 by 6 equation. But it could not be squared, depending, for example, if you have a redundant manipulator, we have 7 actuators, then Q has 7 actuators, so this would be 7 by 1, and J would be a 6 by 7 matrix. For now, again, consider a 6 by 6 and a square matrix. This square matrix can be represented by a number of columns that we call it J1, J2, and Jn, or Ji. Ji is represented for the joint I with respect to the joint I has a zi direction. It would be either a prismatic joint or a revolute joint. As we discussed it from the beginning, we just use the primary joint for the for any robot, and if we have a compound joint, we will basically change it to a primary joint. So we have a primary joint, either prismatic or revolute. If it is prismatic, the Jacobian is very simple. The three last part is 0, and the three first part is this vector zi minus 1. And it could be, again, represented in any frame. Usually we use the 0 frame or base frame to represent this. But as I mentioned, it could be, since this is a vector in the space, it could be considered in any space. It could be considered in n space or in either space. Usually we consider it with the reference frame. For now, consider that. If it is prismatic, it is very simple, zi minus 1 and z0. And why this is the case? Because for a prismatic joint, if you remember, if we go back to here, for a conventional Jacobian, the first part is the velocity of the end effector, and the last part is the angular velocity. And for the prismatic joint, we don't have any angular velocity adding to the system. So this part would be 0. And the linear velocity is along the zi joint. So we have the zi at the top and 0 at the bottom for prismatic joint. But for revolute joint, it is different. Again, for the revolute joint, we know that the angular velocity is about zi minus 1. So the last part is very simple, zi minus 1 for this. But the first problem for the linear velocity would be a cross product of a length to the angular velocity, and we call it zi minus 1 times Pn star I minus 1. This is a notation that the psi has been used. It would be a vector. Let me define the vector, and we should, the most important thing is to find this vector correctly. And quite easily, the most important issue is here. If you understand what is the vector, if you can visualize what is the vector, then it would be very simple to find that. And we don't need multiplication or derivative or finding the forward kinematic to find the Jacobian. We can go through this here. As you see, the zi is very important, so we have to find the zi's. And zi's was very simplified in the Navi-Tartenberg procedure as the axis of rotation or axis of multiplication. But what about this P and I? As you see, Pn star with respect to I minus 1, this vector is as shown in here. The point of interest that we would like to find the Jacobian, let's call it On, the vector that connect from the P and I is defined as a vector, the origin of I minus 1 link. This was for Ji, for the revolute joint J joint, was for a revolute joint J joint I. It has a representation of Zi. It has a OI minus 1. Find the vector of this point to the end effector. That's it. Find the vector of the origin of OI minus 1 to this. Of course, this could be found by intuition, very simple, or it could be found iteratively or by definition. You can find that, okay, this could be found from this vector is if I have Pn and I have Pi minus 1, I can just find this vector by the subtraction of these two vectors. This is another way to do that, which we will be discussing here. But consider that now. The important point is this star n I minus 1 has been put here to make sure that you find the vector that you are finding, Pn, is the point n, the point that you would like to find, the vector, the velocity, with respect to I minus 1. Why I minus 1? I minus 1 is represented to the joint I, is the axis of rotation of joint I minus 1, and y star, not the direct positioning, but the relative positioning. The relative positioning is point from here to here. This vector is of our interest. And this is not very hard to find. We can find it easily in many, many cases. And the rest is just put this, find a number of Jacobians and then put them quite in a column-wise method. And as you go forward, if you see, for example, J1, this vector from here to here has some sort of, if you would like to find, is much more difficult to find, rather than in Jn, the vector from here to here is very simple to find. So usually we start from here and then go back to find all the vectors backwards and find the Jacobian columns in here. That's it. This is the general formulation for any Jacobian. We don't need any velocity propagation, what has been done in Craig, or we don't need to do manipulation of the velocities here. Of course, it has a proof, it has a paper that has been provided that, but we need to find this Pn, and this Pn should be carefully determined by some example. Let me give you an example. Is it clear now? Can we go through the examples? All right. Let's go to some example. Before going to example, I can give a bit more advice if you would like to make it very general. How the I minus 1 can be, if you have the de Navier-Hartenberg, the Paul convention of de Navier-Hartenberg, how we can find the z I minus 1? First of all, as I mentioned, both vectors here, all vectors here should be represented in one specific frame, which we consider for now the 0 frame. The z I minus 1 is always, as you see, is 0, 0, z1 in the frame I minus 1. And if you would like to find it in the frame 0, it is just simple to manipulate that by a rotation matrix from I minus 1 to 0. So the I minus 1 could be found very easily from the kinematic analysis. And P star and I minus 1, as you mentioned here, also this gives you, as I mentioned, you find it the last one. You find Pn from the end one. Let's say I would like to find this vector. Suppose that you want to find this vector. It is easier to find. If you have this vector, you can find it from here to here. If you have this, you can find it from here by this relation. Very simple. The Ri minus 1, which can be find Ri to I minus 1, is the link of the vector, the vector that we would like to find. So it has from the de Navier-Hartenberg, it might have Ai or Di. The Ri minus 1 with respect to I minus 1 is very simplified by this means you can return this to the 0 frame, as we mentioned, by multiplying by R minus 1 to the 0, plus Pn star with respect to I. If you have the frame, the forward frame, you can come back to the back frame by a backward iteration, and you can easily find this in this relation. Let's do that in a general framework. Of course, if the robot is simple, you can by inspection you can find this vector. But if it is very general, if we have AI, we have DI, if we have offset, we have length to link length to the system, then you can find this vector by this kind of iteration, as I mentioned in here. You should Of course, I have written a program to do that. Since it is iteratively, you can also write your program to do that for a different example. Let's go. This example is very important. Again, I put the book here that you can refer to that. From different books, we have find this relation. Again, we are using the Paul convention for the Navier-Hartenberg, not the Craig one. So the examples in Craig's are a bit different from what we are doing in here. The first and most important example is a 3R by RRR, and here I have put the vectors in the important part of the vectors in red, blue, and green, that you can easily find it that way. By a 3 by 3 matrix RRR, we have 3 joint variables, theta 1, theta 2, theta 3. It is a planar case. All of them are along a z-axis, which is out of the plane. And we have the end effector joint variable, which has the velocity, again, x dot or g dot is x e dot, y e dot, and phi dot, which the phi is the orientation of the end effector, while x e and y e are the velocities of the end effector. Now we have both of them all together. We would like to find the Jacobians by this general method. To find the Jacobian, we shall find the zi minus 1 and p star p3, y3, pn, because this 1, 2, 3, the point of interest, suppose is the q1. This point, the origin of the third frame is of our interest. If this is the case, so we need to find P3 star with respect to I minus 1. And this I minus 1, I1, 2, 3, which is 0, 1, and 2, we should find these 3 vectors. And as I mentioned, these 3 vectors are here represented by this red, blue, and green vectors that we can find it. The Zi vectors are very simple in this case. Because it is a planar case, all the revolute joints are along the z-axis, which is out of the plane. And we call it Z0, Z1, and Z2 are all 0, 0, 1 in the frame 0. Of course, we are considering the frame 0. Now, considering the simplest P that you can find is usually the P3 with respect to the 2, the red one. We start with the red one. We don't start with this one. We start with the red one. What would be this frame? What would be this vector in frame 0? Of course, this frame, this vector, is very simple. As you see, it has a length of A3, but A3 in this x3 direction. You see, A3 in a x3 direction. And the x3 direction can be represented in 0, in zeroth frame by theta 1, 2 plus theta 2 plus theta 3 rotation matrix, as we had before. So it is very easy to find that this would be A3 cosine of that. The component of that in x direction is cosine of the theta 1, theta 2, theta 3, and this is simply with respect to that. So we can find this either by intuition, as I mentioned, or going through this way. We can say that, okay, this is very simple. We don't have P star by N. This would be 0. This is our I minus 1 is, as you see, AI cosine of theta I, AI sine of theta I, DI is 0 in this case, and then just multiply it by rotation matrix from 2 to here, which gives you this part very easily. Do you agree with me? Are you following me? This vector has a length of A3, and component-wise, the cosine and the sine of the angle of rotation. And we would like to do it. This angular rotation is exactly phi, but we are using the theta values for pi to find that. If you have found this, then it is easy to find this vector and this vector. You have found this vector. Now, if you have this vector plus this vector, this gives you the P32I. And you see that this vector, A3, this part, could be added by this vector. This vector has a length of A2 in the theta 2 plus theta 1 direction, theta 2 plus theta 1. So we add this two part to this, we can find this easily. This is done by intuition, very simple. Of course, you can use this iteration as well, but I will do that for a more sophisticated problem. For this case, it is very easy. As you see, this vector plus this vector are in a plane. You add both of them component-wise in theta 0. And it was much easier if instead of finding in 0 frame, if we find it in the 3rd frame, everything in the 3rd frame, it would be much simpler. The Jacobian would become much simpler. But here we are finding it in the 0 frame. And the last, but not the least one, is the green vector. The green vector 3 would be this vector plus this vector. We had this vector, which we call it P3, with respect to I1. It means that with respect to frame 1, now with respect to frame A1, cosine of theta 1 and sine of theta 1 will be added to the system. And this can be easily put together. Now we have this one, we have these 3 vectors. The only thing is we have to cross multiply that Zi to P star n to find the Jacobian. And if you see, here we would have a 6 by 3 vector, but we only use the 2 first part here. If you multiply Zi, it is very easy. We have a vector here, P, a vector in this vector here. So these 2 vectors, when they are cross-multiplied, give you a vector in x and y direction only. So we have in x and y direction. And the Z1, 0, 0, 1, it would be that, as you see here, we have 0, 0, 1 here. We just use the last component, the phi component here, to have a 3 by 3 matrix. So just multiplying this through Zi will give you this one. Multiplying this to Zi will give you this part. And this one to Zi will give you these 2 parts that we decompose in x and y direction. And as you see, it is quite, again, sophisticated. It is quite large since we are representing it in 0 frame. And I would like to ask you to find the Jacobian in the nth frame, in the 3rd frame, not by multiplying it by rotation matrix, doing the same way, finding the vectors, all the vectors in the 3rd frame, and doing the multiplication in the 3rd frame. Anyways, now this is the Jacobian matrix for the Q frame, for the end effector point. We can do the same thing for the wrist frame as well. If the velocity of this point is of our interest, then the last part will be diminished, is not used. We have only 2R manipulator, and the Jacobian will be reduced to very similar to this, but the theta 3 will be out of the frame and out of the question. It could be found quite easily. Again, here, the most important part was the P star 3 with respect to 1, 2, and 0 frame. We should find 3 vectors to find the 3 column vectors. And it was a bit intuitive here to find that. Any question here? Let's go to another example. Again, this example is been developed both in the TSI and the also Spunk book, Skara has a 4 by 4 equation. Of course, here it is not a 3 by 3, it is not a planar, so the Jacobian we will find will be a 4 by 6 equation, but 2 columns of that, 2 rows of that is equal to 0. Anyways, this is different since the Jacobian is not squared, and we should think about it. But as we denote, we have 4 variables, as you see. Just to remind you the Skara, it has a θ1, a θ2, and then we have a d3, and the θ4 for the orientation of the last term. So θ1, θ2, d dot 3 and θ dot 4 are the velocity vector in the joint space. What would be the end effector? It gives us a x by z in the end effector, and a omega e, which of course it's not a complete orientation. It has only 1 degree of orientation. Omega e has a component around z4, for example, to this component. Of course, we have found the Navier-Hartenberg parameters in the previous section, and also the transformation we have found all before. Now we would like to go to the Jacobian. We should find the zi's and p star. These 2 are important. Now we go one by one. Again, here, since the robot is simple, we can find it, the P stars, much easy by intuition. Somehow intuition, a bit more than the previous case. The ZIs are very simple. As you see, when we have the ZIs all here, Z0 and Z1 are along Z0 if we have the base frame, so it is 0, 0, 1. But Z2 and Z3, as you see, are in the other direction, are 0, 0, minus 1. This is because of the definition of the Navier-Hartenberg that we have considered D3 coming downward as the positive relation that we have here. Again, we would like to find the P stars, and the P stars here in this figure I showed the first to last one. We start with the last one. If the point of interest is the velocity is q, we would like to find the red vector and the purple one, which is the difference between these 2 vectors from frame 4 to frame 3, P4 with respect to frame 3. We call it the star one, the vector of interest that gives us the velocity, or the frame 4 with respect to 2. This is the red one and this is the purple one. And as you see, this is D3 in Z4 direction, and in Z0 direction is minus D4. Very simple. And again, D3 plus D4 in Z4 direction, but in Z0 direction it would be minus D3 to ZD4 in this direction. Again, it is also possible to find all these vectors in the last frame, and it makes the life much easier, but for now I do it with the first frame, and I would like to use these rotation matrices here. These 2 are simple, but the other 2, because it comes out of the plane, then we have some other portion to it. Let me just show you these 2 frames. Now that we have this purple frame, if we would like to find it to the other joint, I should find this one and add these 2 together to find P4 with respect to the first frame. P4 with respect to first frame 1. What I did is I just used that iterative method that I showed you, but physically, to give you the frame. I said, okay, I have P4 with respect to 2. This purple one has been found here. We have P4 with respect to 2. We should add this vector to it, but considering that this vector should be all represented in the 0 frame. This vector, as you see, is the link of the vector is along the x frame in frame 1 or frame 2 in the joint 1, and we should basically find from here to here this vector. It would be A2, 0, 0 in the frame 1, but we should just bring it into the 0 frame. Since we have a motion there, we just multiply it by R2 with respect to 0. So by multiplying this and adding to this vector, just simply we can find this. We have also z direction and we have x and y direction as well. And finally, the blue vector here, the blue vector could be considered as the addition of these two frames. Now we have this frame, we can add these two together. Again, as you see, this vector has a direction A1 in x direction and a D1 in z direction. As you see, we multiply it by R1 to 0 to bring it to the 0 frame, plus this vector, the previous vector that we have found here. Very simple. And what we are doing here, if you look at it, is exactly what is represented in this here. We have the R1 multiplied by the rotation matrix and added with the previous vector. This has been done in an iterative way. As you see, again, P4 with respect to 3, P4 with respect to 2, then P4 with respect to 1, and P4 with respect to 0. Now we have all the vectors available. We just cross-multiply these two together and find, since we have 3 revolute and 1 prismatic joint, you see 4 revolute and 1 prismatic joint. This prismatic joint gives you the Z3 to 0 here. And you find the multiplication here. Although the P1s are too heavily defined and too sophisticated, the multiplications are quite simple and easy. And you see that we can have this part quite well known. The angular velocity is fine, θ1, θ2 minus θ.4 in z direction. As you see, the angular velocity can be found. As you see, these two parts are 0. This gives us the angular velocity part. This gives us the linear velocity part. The linear velocity would be this part plus the z direction of the prismatic joint. The angular velocity has no x and y direction, has only z direction, and it is θ1 plus θ2 minus θ4, which is intuitively quite right because of the angle of rotation that are adding up altogether. Although we have a 6 by 6 matrix here, we can just reduce these 4 rows. We can find the 4 by 4 Jacobian matrix that can relate these two basically to each other. The WE would be in z direction, as you see in here. This is a really sophisticated Jacobian matrix, and if you would like to find the forward kinematic and just make the derivative of all terms, it would be much more harder issue to work with. Well, all right, any questions? Yes, Hossein, please. Please, Hossein.
Okay, good morning.
Good morning.
I have a general question. You talked about actuators and joints. Maybe I have a robot with the number of joints more than the number of actuators.
Yes.
When talking about screw axis or Jacobian, I must take in consideration the number of joints or the number of actuators?
The number of joints and actuators in serial manipulators are usually the same. We have a joint, we are actuating it. And if we have more joint than we require, let's say we have 7 joints for a 6 degree of freedom manipulator, you have the number of joints, and the number of joints, as you see, will give you the number of the columns here. If you have a redundant manipulator, we call it a redundant manipulator, the number of joints or the number of actuators, these are usually the same. We have a joint, we add a joint to actuate it, otherwise it doesn't really matter in serial manipulator. In parallel manipulator it is totally different, but here if you're adding a joint, you're adding an actuator. The number of joints, we can say, as you see, gives you the number of the columns as you see. The number of queues gives you the number of joints, the number of columns here. But the number of rows, as you see, is the number of degrees of freedom of the robot. So if we will see that in some part of the same chapter. If we have a non-square matrix, we can finding it is quite easily. You have, instead of having 6 joints or 4 joints like what we have in SCARA here, you can have, as you see here, in the SCARA we have, as you see, we have 4 here. If you have another joint, 5th one, we add another one. If you have a 6th one, we add another row to this case. Okay. Now, let's go to the last example. We don't have that much time. I don't go through all the details here, but it is quite easy to find that. And in here, again, instead of finding the manipulator endpoint Jacobian, just to make it different from the previous one, we find the wrist point for the Stanford manipulator. As you recall, Stanford manipulator was a RRR manipulator. We have 6 degrees of freedom. We have 2 rotation matrices at the beginning, 1 prismatic one, and then 3 angular velocities or angular rotary one. And x would be x dot, the velocity of point P. It could be the point Q, but we intentionally consider the point wrist point here to make it much easier and also different from the other one. And the angular velocity that we can get in here. As you see, if we consider this point, the upper part doesn't come into the picture because we are only considering the velocity of this point. And if you consider the Q point, the end effector, then all the joints will be considered in here. Again, very simply, we can have the Delawitt-Hartenberg parameters. We have the transformation. We have also the kinematic, the forward kinematic before. But we would like to use the general method to find the Jacobian. And the Jacobians can be found by this means quite easily. First of all, find the ZI1 through ZIN. The ZI1 is 0, 0, 1 with respect to the frame 0. But Z1, 2, as you see here, will have a theta angle rotation with respect to theta 2 angle rotation with respect to theta 1, and this makes the Z1 equal to minus S theta C theta. We use the rotation matrix. We cannot find all of them quite simple as before, but it is not very hard. We have the Z1 multiplied by the rotation matrix, we find the Z in 0 direction. Again, Z2 and Z3, Z2 and Z3 are in this direction. In the frame 2, there are 0, 0, 1. We just multiply it by R2 with respect to 0. We bring it to 0 direction. So the ZIs are found well. Z4 and Z5 is found also with the same intonation in the same way. They are quite long. Now we should find the P stars one, which are more complicated here. To find that, P6 to I minus 1, since we are using P at this point, the ending points that comes to here are all, we consider all of them 0 because we don't have any velocity on top of that. We are using this point as the only P6 through 2, 1, and 0 shall be defined in here. Of course, if we would like to find the velocity of the end effector, we should also find all these three vectors, which makes the life much more harder. But here we just consider the wrist, and since the wrists are on the third vector, on the Z4, on the third joint, on the Z4 actuator, basically, and then we can find it from here. Here we have only two vectors, the red one and the green one, that can be easily find from 3 to 2. Let's say the P6 to 2, since these three are all equal to 0, all of them are here. This vector P6 is the red one. This red vector is the D3 vector that can be multiplied by R2 to 0 to bring it to the 0, 1. So the D3 vector will be multiplied by R2 to 0. As we had it here, it will be very simply find this way. Now we have this one. We would like to find the green one. We have this one plus this one. We can find this vector D2 in Z direction, multiply it back into the rotation matrix, and add these two all together. And then we can find this one. As you see, we have this one plus D2, which is multiplied by the R2 with respect to 1, and this comes to here. And then finally the 0 vector. The 0 vector, since Z1 and Z2 are both the same, at the same point, they are intersecting, these two equations, these two P's are equal to each other. So we have 3 vectors and 3 of them 0. We have 6 Z's, and then we just multiply that again with the same idea here. We have 6 components, Zi cross P star N, and Zi minus 1, the prismatic joint. And as you see here, the final solution, the third one, since the I is here, this is Zi and 0, but the other ones, these are Z1, Z2, Z3, Z4, and Z5. As we see in here, this is Z3, and then the multiplication of the PI star here. Since the PIs are 0 from 3 to 4, this doesn't contribute in the velocity, but this one will contribute in the velocities quite well. And we find the velocities quite naturally by this means. Okay, I would stop in here, and we'll give the solution to the screw-based Jacobians in the next session. And it is very, very important to know that the columns that we are now working with so hard are nothing but the screw axis representation, and that makes the life much easier in the next session. Is there any question? Please contribute. Okay, if there is no question, please consider having your first, the second assignment done by the beginning of the deadline the next week, and as you see, these questions are the assignments are put together as two simple questions and one more sophisticated one. The third one is a project based, and you continue these three examples hopefully in the other assignments that we have. Please considering giving you the research and also the assignment on time, that we can continue with the course quite easily. Thank you very much for joining us and have a good day. موفق باشید بچه‌ها. آرزوی توفیق و سلامتی دارم برای شما. خدا نگهدار.